December 18th. Oh my, where did the year go? But we're closing with a biggie here. We got John Siegenthaler is going to join us today. If there's a guru in our industry, Siggy's the guy. So this is going to be a two-part webinar that we're going to do. Of course, the first part today on designs and calculations, and the next part you'll get a little bit more into pumps and pump selections and stuff like that. So you really need to watch both of them. But I think we got a lot to cover, so I'm going to turn it over. Thanks, Siggy, for coming on board today. And let's see what we got.
Oh, you're welcome. Good to be here, Hot Rod. And I just want to point out today's topics are coming out of Hydronics. We've got a new issue coming out in January, number 16. Here's a listing of all the previous issues of Hydronics. And as I mentioned, number 16, that'll be out at the AHR show at the end of January. And the topic is circulation in hydronic systems. And today's webinar is taking some topics out of that. Basically, the first part of the two-part webinar series is going to talk about head loss in piping systems, and then January 22nd, part number 2 will get into specifics on how to size circulators and how to use some of the new smart circulators to their best advantage. So, specific topics for today. The word head is probably a good key word for today's Coffee with Caleffi. What is head in the context of a hydronic system? How do we measure it? How do we work with it? What's the relationship between head and pressure? They are related, but they're not the same thing, and I want to clear up some misconceptions on that. We're also going to be talking about basic terminology that quantifies what's happening in hydronic systems, flow rate and flow velocity. Oftentimes we hear the word flow or flow speed or something like this. Again, flow rate and flow velocity are related to each other, but they're not the same thing. We're going to talk about fluid-filled hydronic circuits. These are by far the most common type of circuits where the circuit is entirely filled with a liquid and we're circulating that fluid around. There are some characteristics that apply to that. There are some circuits that are not filled. The drain-back solar system is a good example of that, or perhaps a cooling tower system. We're not going to get into those today, but we will talk about them in the future. Then we're going to get into some of the math, the classic relationship between head loss and flow rate. As the flow rate through a hydronic circuit increases, the head loss increases, and we need to have numbers to describe that. And we'll talk about kind of the classic way to do that as well as a simplified way to deal with that. That applies in residential, like commercial systems, where we're using smooth piping, copper tubing, PEX aluminum PEX tubing. We can simplify some of the mathematics. We're going to talk about, in the process of simplifying the calculation of head loss, fluid properties, equivalent lengths. Again, these are essentially numbers that we have to gather up and process through an equation to calculate a head loss. And then we're going to look at a circuit head loss curve. Think about every hydronic circuit you've ever designed or ever will design. Every one of those circuits has a head loss curve. Just a matter of making some calculations to know what it is. I like to describe a head loss curve as the fingerprint of a hydronic circuit, because every circuit has one and it's unique to that circuit. We're also going to draw an analogy between electrical circuits and hydraulic circuits or hydronic circuits. The concept of resistance. If you've worked with electricity, I'm sure you know Ohm's law, and you know that you have resistances in electrical circuits. Those resistances can be combined. Sometimes they're in series. Other times they're in parallel. But we're going to draw an analogy to that with a hydronic circuit. It's a very powerful way to look at hydronic circuits, and it's a way to analyze those circuits. So in short, today's presentation is about running numbers. We're going to look at some math, and it's straightforward math. It's all math that you can actually do on your iPhone if you wanted to. And we're also doing this because we want to make estimates. I don't want to imply that a calculation is always 100% accurate, but it's better than a guess. So today is about giving you tools that allow you to estimate the performance of hydronic circuits reasonably well, so you don't have to guess. So let's move on to flow rate and flow velocity. We'll start with flow rate. It's a measurement of the volume of fluid passing a given point in the system per unit of time. That's kind of the classic physics definition. So imagine we could identify a point in a hydronic circuit, and we're going to measure how many gallons of fluid pass by that point per minute. There's other units we could use, but commonly in North America, gallons per minute is the standard for that. Now, flow velocity is a little bit more complex. I've got down here that flow velocity is the average velocity of a fluid particle moving through a pipe. And here's kind of a picture of what's going on. This is a cross-section of a pipe. Flow is going from left to right here. And I want you to imagine those little red dots that you see here. Think of these as what I call buoyancy neutral particles. Think of these as something that you could instantaneously place into the flow stream and then watch how they move. What you would find is that these little particles are going to actually move faster near the center of that pipe. And as you move farther out towards the wall of the pipe, their velocity is going to go down. And you can see this in other situations where a fluid is moving. A river is a good example. The next time you look at a river, look at the water moving down through the center of that river versus the water moving near the edge, near the banks. And you'll see the water moves faster near the center. So you might say, well, if all these particles, so to speak, and these could represent molecules of fluid, if they're all moving at different flow velocities, how can we state a number? Well, we have to average it. Okay, and over here on the right, if we could imagine that all these fluid particles or molecules of fluid are moving at the same velocity, or let's state it this way, they're moving at a velocity so that in a given amount of time, the same amount of fluid will pass a given point in the piping system as would actually be the case when they're all moving at different velocities. So if you look at that curve right there that I'm tracing with the cursor, that's the actual velocity profile. And what I'm showing here with these equal length arrows represents a hypothetical situation, but it represents average flow velocity. So later on, when we talk about flow velocities like 2 feet per second or 4 feet per second, we're talking about average. We're not talking about how fast it's moving at the center or at the edge or anywhere in between. We're just talking about an average. Okay? And in 3 dimensions, it would look sort of like a nose cone. We're looking at it in 2 dimensions here on the left and the right, but just imagine we could rotate that parabola around and make that nose cone. So the very fastest fluid is moving right down the center line of the pipe. Okay? Now, to calculate average flow velocity in a pipe, it's actually pretty straightforward. This table shows several different sizes and types of pipe. I've got type M copper, PEX in sizes from 3/8 up to 2 inch, and PEX aluminum PEX. And you'll see for each one of those tube sizes, there is an equation over here on the right side of the table. And it's a simple formula. And here's an example of how you would use it. Let's say you wanted to know the average flow velocity associated with a flow rate of 9 GPM moving through a 1-inch PEX tube. But we come over here for 1-inch PEX, we'd find our formula, and we just substitute in. We just take that number, 0.533, multiply it by the flow rate, and that gives us the flow velocity in feet per second. Again, when you're using any type of a formula, you want to make sure you understand the units that are implied in that formula. And in this case, we're using flow rate in gallons per minute and flow velocity in feet per second. And that'll be the case throughout the webinar. Occasionally, you might run into a pipe where you don't have a formula in a table like this. And here's a generalized formula. As long as you know the inside diameter of that pipe, and it's assuming a circular cross-section, you know the inside diameter, you square it, divide it into 0.408, and then multiply that number by the flow rate in gallons per minute. That'll give you the average flow velocity. So again, moving back and forth between flow rate and flow velocity, as long as you know the tube that you're dealing with, it's a pretty simple calculation. Let's move on to talk about sizing a pipe. There are several issues that come into play here. One of those issues is air entrainment. If we move water extremely slow through a pipe, especially a pipe that's vertical where the flow is moving down, you can imagine that bubbles, especially larger bubbles, can actually move upward faster than the liquid is moving down. And we don't want that. In general, we want to be able to entrain air bubbles. We want to be able to drag them along with the liquid and eventually bring them back to an air separating device and capture them and eject them out of the system. Generally accepted practice is to size your piping for a minimum flow velocity of 2 feet per second. And that is based on a vertical pipe with downward flow, and it's considered the minimum velocity at which we can effectively entrain air bubbles and bring them along with the flow. Okay. Now, another consideration is flow noise. And in smaller pipes, and I'll define it, we're talking about 2-inch and smaller nominal pipe diameters. A general guideline is to size for a maximum flow velocity of 4 feet per second. And again, the criteria here is to avoid objectionable levels of noise. There's always some detectable noise if you have the right instruments, but in a space with human occupancy, let's say we have a baseboard and we have water flowing through it, we don't want to hear that water moving through that baseboard. And keeping the flow velocity under 4 feet per second is a good criteria for that. The graph that's here shows you head loss versus flow rate for several smaller tubes here from 1/2 inch all the way up to 2 inch, and this is for type M copper. We're going to get into the head loss part of it in a minute, but I want you to notice this black curve. That shows you the condition at which each of those tubes has a flow velocity of 4 feet per second. So, for example, at roughly about 3 gallons per minute or just under 3 gallons per minute, a 1/2 inch tube has a flow velocity of 4 feet per second. All right? If we wanted to know how much water can we pass through, let's say, a 2-inch copper tube and not exceed 4 feet per second, well, you can see it here. It's almost 40 gallons per minute. I want you to notice that curve drops down quickly. Okay, and that will play into how we size larger pipes. When we get above 2-inch, a criteria that, again, is common practice, it's actually mentioned in the ASHRAE handbooks, is to change our sizing criteria from the 4 feet per second to what's called specific head loss. And specific head loss refers to a number, a feet of head loss per 100 feet of pipe. And the suggested range here is from 3 to 5 feet of head loss per 100 feet of pipe. What that does is it prevents these larger pipes from being grossly oversized. If we were to stay with the 4 feet per second criteria all the way up to, let's say, 6-inch pipe or maybe even beyond 6-inch pipe, we will have pipes that have extremely low head loss, but economically they're going to get very expensive for the amount of flow. So basically, at that 2-inch nominal size is where we change from the 4 feet per second criteria over to the head loss, specific head loss of 3 to 5 feet of head loss per 100 feet of pipe. Now, you might say, well, how do I know between 3 and 5? I would tell you if your design objective is to minimize pumping power, you'd probably go at the lower end of this range, 3 feet of head loss per 100 feet of pipe. If your primary design objective is to keep the cost as low as possible, go towards the other end. So there's a trade-off there, and you have to look at the project and think about what you're trying to accomplish and then and base your decision on that. Now, another condition we have to be aware of is a minimum flow rate that will affect heat transfer. In most hydronic systems, we're passing a heated fluid through a device, and we want heat to move from that heated fluid into that device and eventually out into the space. In a cooling system, it'd be just the opposite. We want to absorb heat through that tube wall into the chilled fluid. And the condition under which that flow is moving through that pipe will have a marked effect on how effective that heat transfer is. One of the conditions that flow can exist under is called laminar flow. And laminar flow, think of it this way. Again, think of each of these little red dots as a fluid molecule. You'll notice that they're all moving in parallel lines. Okay, they're all moving in streamlines. A streamline is just a path that an imaginary fluid particle or a molecule of fluid moves along. With laminar flow, the streamlines are all parallel. And you can almost think of this as sort of telescopic cylinders, the way this shows down here. Again, the molecules near the center of the pipe are moving faster. Okay, then the molecules that are closer to the edge of the pipe or the inner wall of the pipe, but they aren't mixing. They're all flowing in these parallel paths. It's sort of like many, many lanes on a highway where none of the cars are changing lanes. Everything's staying in the same lane. Now, we can contrast that with turbulent flow. In turbulent flow, again, if you think of these red dots as cars on a multi-lane highway, they're driving sort of like people up there, I guess, maybe in New York City or Milwaukee or Toronto. They're crossing lanes very, very abruptly. And you can see there's a lot of mixing going on. And from the standpoint of heat transfer, mixing is good. So turbulent flow is what we're looking for. And to explain why, let's take a look again inside a pipe. Here's our velocity profile. Again, the fluid molecules near the center of the pipe are moving faster than the ones out near the edge. And it's a little tough to see this, but if you look really close, you'll see a little light blue line right there between the pink fluid and that darker brown color that represents the wall of the pipe. That very thin layer of fluid is called a boundary layer. And it might only be a few thousandths of an inch thick, but I want you to think of that as sort of like liquid insulation. It is presenting a resistance to heat transfer between the bulk of the fluid and the tube wall, in the case of moving heat from a hotter fluid to a cooler tube wall. The thinner the boundary layer is, the better the heat is able to move from the bulk of the fluid, the core of the fluid stream, as it states down here, into the sidewall of that pipe. The way we make the boundary layer thin is basically to create turbulent flow, because as those fluid molecules basically come up near that wall of the pipe, if they're moving in a very haphazard way, it's sort of like sandblasting on the inside of the pipe. They're going to thin the boundary layer, and that's going to improve heat transfer. It's always the case. The faster the fluid moves through any device, the better the heat transfer is going to be. There's no such thing as moving a fluid, from the standpoint of heat transfer, there's no such thing as moving the fluid too fast. Now, there's other things that are a problem when you move the fluid too fast. Pumping power can be very, very high, and even erosion of the material. But from a pure heat transfer standpoint, the faster the fluid is moving, the thinner the boundary layer, and the better the heat transfer. So how do you know whether you have laminar flow or turbulent flow? Well, we're going to predict that based on something called Reynolds number. And this is where we start to do a few calculations, okay? The Reynolds number is called a dimensionless parameter. And that means that when we calculate it, there aren't any units that are left over when we make the calculation. I'll walk you through that. There's 4 things that you need to know to calculate the Reynolds number of a flow. You need to know the velocity. That's the average flow velocity that we were talking about a few minutes ago. You need to know the inside diameter of the pipe. You need to know the density of the fluid in pounds per cubic foot. And you also need to know something called dynamic viscosity. And I'm sure many of you have heard the word viscosity, probably in the context of oil. Think of viscosity as a property that is indicative of the ability of the fluid to move easily. High viscosity fluids like a very cold motor oil will flow relatively slowly. When we heat a fluid up, we lower its viscosity and it flows faster. And of course, you can see that with something like motor oil. Once you warm it up, it appears, typically the term is thinner, but in fact, it's just has a lower viscosity. Well, when we heat water, its viscosity changes considerably, and it's easier to move heated water through a piping circuit than it is to move cold water, and the reason is viscosity. So if we put these together, we calculate the Reynolds number. Now, you might say, well, how do I know what these numbers are? Well, 2 of them you can read right off of these graphs here. This is a graph for the density of water, where we just look up the temperature of the water, go up to the red curve and read over here, and we get density in pounds per cubic foot. The other graph shows the dynamic viscosity of water. Same idea. You find the water temperature, you go up to the curve, and you read over. And notice these are very small numbers, and they have peculiar units, pounds per foot per second. Very important when you put numbers into a formula like this that they all cancel out. And I want to show you an example of that. Here's where we're substituting in the units for these different parameters. So for velocity, feet per second. For the diameter of the pipe, feet. Now you might say, well, pipe sizes are given in inches. That's true. Convert it to feet. Just divide by 12. Okay? Very important. Density is in pounds per cubic foot. And then again, the units on dynamic viscosity, pound per foot per second. Now, if you carefully go through here and you do the algebraic cancellation of the units, you'll see all these slash marks on these units here. What happens is they all cancel out. In other words, you're going to get a pure number for the Reynolds number. There's no such thing as a Reynolds number, something like 4,000 feet or 4,000 feet per second or 4,000 anything. It's just 4,000. If you calculate the Reynolds number in metric units, it's got to come out a pure number as well. That's why it's called a dimensionless parameter. Okay? And this is a check. If you're ever calculating a Reynolds number and you come out with some units that do not cancel out, you have units left over, something is wrong. And it could be that you didn't convert the diameter into feet before you plugged it into this formula. So it's a way to check your calculations. Now, once you calculate that number, you can determine whether the flow through the pipe is laminar or turbulent. If the Reynolds number is 4,000 or higher, the flow is going to be turbulent. If the Reynolds number is 2,300 or less, the flow is going to be laminar. You might say, well, what happens in between? Well, it's a zone of uncertainty. The Reynolds numbers between 2,300 and 4,000, the flow could be laminar or it could be turbulent. It's an unstable flow regime is the term that's used. And generally, we don't want to be there, especially if we're trying to transfer heat through our tubing. We want to have Reynolds numbers that, in general, are well above 4,000. Okay? And you'll see that in many cases, if you look at common flow rates in things like 3/4 inch copper tubing, maybe at 5 or 6 gallons per minute flow rate, you'll see the Reynolds numbers in general, they're even over 10,000. So we're assured of having turbulent flow and good heat transfer. Now, I rearranged the formula a little. If you want to know the minimum flow rate for a given tube size and a given fluid, that will give you a Reynolds number of 4,000. And remember, this is our criteria, minimum criteria for turbulent flow. This formula will do it for you. Okay, we take the viscosity of the fluid here. Again, we just read it off our graph. The internal diameter of the tube and the density of the fluid. Again, I've given you graphs for density and dynamic viscosity for water. You might say, how about if I'm using antifreeze? Well, go to manufacturer's literature, for example, Dow Chemical for Dow Frost, propylene glycol. They have an online PDF file that you can download. It has all this data for the different concentrations of their propylene glycol product in water, and you can get the numbers from that. Okay. I did an example calculation here. What's the minimum flow rate for turbulence in a 1/2 inch copper tube that's moving water at 120 degrees Fahrenheit? And the numbers work out to be just over 0.4 or 0.4 of 1 gallon per minute. Okay? So if you're sizing baseboard and you have a 1/2 inch tubing, you want to make sure that the flow going through that tubing is turbulent. You want to transfer heat well. So flow rates of less than 0.4 of a gallon per minute through a 1/2 inch copper tube in a baseboard would not be a good thing from a heat transfer standpoint. That heat transfer is going to drop off significantly if the flow is laminar versus turbulent. Remember that boundary layer. We're trying to scrub that boundary layer as thin as possible. I also ran the number here for a 3/4 inch copper tube. It's a common tube used in our residential systems. With 120 degree water, it works out to be a 0.57 GPM. Okay? One of the things I'd encourage you to do if you want to experiment with this is calculate the minimum flow rates for cold water and compare it to the results that I've given you here for 120-degree water. What you will find with cold water, and you can actually see this in this graph, the dynamic viscosity, as we get down into the 50, 60, 70-degree temperature range, you can see it goes up very, very quickly. And that implies that the flow rate of cold fluid to maintain turbulent flow, it goes up considerably. And this is really important if you're doing, for example, an earth loop, and you're running a 20% propylene glycol solution through an earth loop at low temperatures, maybe 30 or 40 degrees Fahrenheit. You have to have a minimum flow rate in order to ensure that you have turbulence inside that tube and therefore getting good heat transfer. So be careful on the low temperature side of things. Now let's move over into this term head. Okay, there's a lot of confusion, has been for years, for what this term actually means in the context of hydronics. The best answer, and I think the most accurate answer, is head is mechanical energy. When we talk about the head of a fluid, we're talking about the mechanical energy that fluid contains. And it's based on a very classic equation from physics called Bernoulli's equation. And one way to write Bernoulli's equation down is this, that the total head energy that a fluid contains, there's actually three ways that it can contain head. The first one is based on its pressure. If we know its pressure in pounds per square inch, we multiply it by 144 and divide by the density. That gives us what we call pressure head. So one of the ways that a fluid contains mechanical energy is that it is under pressure. Another way a fluid contains mechanical energy is based on its movement. All right, if that fluid is moving, it contains kinetic energy. And if you think back to those of you that have taken physics, anything that's moving, any mass that's moving has kinetic energy. And this is how we would calculate it for a fluid. And then finally, a fluid can possess mechanical energy based on its elevation. If a fluid is up high relative to the surface of the earth, it has more energy based on that position relative to the fluid being closer to the surface of the earth. So a fluid, the total amount of head, is based on the sum of these three: pressure head, velocity head, and elevation head. And the interesting thing is fluids can trade this energy back and forth. If a fluid slows down as it moves through a pipe, it's going to give up some velocity head, and what will happen is its pressure will increase. Or vice versa. This is how a venturi works. So there's a lot of interesting physics that is based on this. And the units that we're going to calculate for head, now many of you that have worked with this concept know that the units that we commonly use for head are feet, or sometimes I'd like to state it, feet of head. And I do that to distinguish between feet as a unit of distance and feet as a unit of head. So the best way I can explain this to you is that if you think about the concept of foot-pounds, foot-pounds, that's a unit of energy. You can convert foot-pounds into BTUs. You could convert foot-pounds into kilowatt-hours. You could convert foot-pounds into joules. It's a unit of energy. What the head of a fluid is how many foot-pounds of mechanical energy is contained in each pound of that fluid. Okay, so think about a pound of fluid. That's, in the case of water, it's roughly a pint. At some location in the system, there's a certain amount of foot-pounds of mechanical energy based on its elevation, its speed, and its pressure. Okay, so what happens mathematically here is that the pounds cancel out, and that's where the unit of foot comes from. My preference is to actually keep the units like this and describe the head of a fluid as the number of foot-pounds of mechanical energy each pound of fluid contains. And here it is, actually algebraically a little more, a better format. You can see where the pounds cancel out, just give us feet here. Okay. Here's another misconception, that head and pressure essentially mean the same thing. Well, they don't. It's like heat and temperature. Heat and temperature are related, but they're not the same thing. And the best way to think about this is as follows. Whenever the pressure of a fluid increases, that's the evidence that head energy has been added to it. Okay? In other words, an increase in pressure is the evidence that head energy has been added to a fluid. Think about water now going through a boiler. Water comes into the boiler at some temperature. Maybe it comes in at 140 degrees Fahrenheit, and it leaves at 150 degrees Fahrenheit. How do we know that we've added heat to that water? We can't see heat, okay? But we can certainly see the evidence that the temperature has increased. So just like an increase in temperature is the evidence that we've added thermal energy or heat to the fluid, an increase in pressure is the evidence that head energy has been added. And vice versa, a decrease in pressure is the evidence that head energy has been removed from the fluid. And here's kind of a picture of what's going on. Let's start with a circulator. A circulator is the only device in a hydronic circuit that actually adds head energy to a fluid. We could describe a circulator as an energy converter. We're converting electrical energy that we supply the circulator into mechanical energy, which we happen to call head. And the evidence that that circulator is adding head energy is an increase in pressure. So the fluid goes in here at 12 psi, and it comes out at 18 psi. An increase in pressure is the evidence that head energy has been added. Now, everything else that fluid moves through in the system, piping, fittings, valves, heat emitters, heat exchangers, boilers, radiators, anything else it moves through dissipates that head energy. And that happens because those fluid molecules are basically bumping into each other as they move along through the piping system. They're also bumping into the surfaces of these components. And that all creates friction. And friction ultimately takes mechanical energy and converts it into heat, just like the brakes in your car convert the kinetic energy that the car has when it's moving down the road. It takes that energy away and converts it into heat. Here's the relationship between the pressure increase or decrease that you'd measure across a device and the head, the exchange of head energy. If we take the differential pressure here and let me start this way. Let's take the head that we've added to the fluid. We multiply it by the density of the fluid and divide by 144. That'll tell us the increase in pressure in the case of a circulator. And this formula also works for the removal of head. If we know that our pressure dropped by, in this case, 3 psi, and we knew the density of the fluid, we could calculate how much head energy was taken away. And keep in mind, you can do some algebra on this fluid. I've got it set up where we're calculating differential pressure or pressure change based on knowing the head. But if we want to know the head and we know the differential pressure, we multiply this side by 144 and divide by D, and that'll give us head. Okay? I do want to point out that oftentimes people convert between head and differential pressure just by multiplying by, typically they'll take the pounds per square inch pressure and multiply it by 2.3 or 2.31. That's an approximation. It's based on cold water, but it's only an approximation, and it only is really valid for cold water. When we're working with other fluids, as we saw earlier, the density of a fluid changes not only by its chemical nature. If we're working with an antifreeze solution versus water, they're going to have two different densities. And both of those densities are going to depend on the temperature. So the accurate way to convert between head and differential pressure, you really have to know the fluid you're working with and at least an approximation of its temperature in that system. Let's say it's average temperature. Okay? Now, fluid-filled piping circuits. All right, here's a really simple piping circuit. Okay, and let's say that I tell you that piping circuit was 100 feet tall. Some people, if they were asked to go out and size that circulator, would show up at the wholesaler and say, give me a circulator that has a head of 100 feet or more. And they're going to grossly oversize the circulator because they're making the assumption that that circulator has to lift the fluid all the way up to the top of that circuit. That's not what's going on here. We're going to fill this circuit with other means. We might use city water pressure as an example to push the fluid up and get the air out of the piping, and at that point we have a fluid-filled piping circuit. All right, now, let's start down here at the bottom. We can say that there's a certain static pressure due to the height of this fluid column here at A, and we have the same static pressure down here at B. So basically the static pressure on each side is balanced. All right, now we turn the circulator on, and the circulator starts pushing fluid up this side. All right. The flow rate that goes up the left-hand side must match the flow rate that comes down the right-hand side. It's impossible to have a difference, assuming you don't have a leak in the circuit. All right, so if we were moving 10 gallons of liquid up this side per minute, 10 gallons per minute of liquid has to be coming down over here. If only 9 gallons per minute is coming down and 10 is going up, I'm going to tell you somewhere you have a leak, and it's leaking at a rate of 1 gallon per minute. So again, we're assuming no leaks, and we're assuming the fluid is filling the circuit. We're also assuming, and this is a very valid assumption, that water is incompressible. Most liquids are incompressible. That means we can't squeeze them, we can't stretch them without tremendously high forces. Forces way beyond what we can exert on them with circulators. So we can't say that we can compress the water together on one side of the circuit and have it stretch out on the other or anything like that. All right? And this is true regardless of what the pipe sizes are. So over here on the right, I've purposely drawn kind of a wacky circuit that has all different kinds of pipe sizes in it. But the same principle holds true. If we had 10 gallons per minute moving up the left side, we have to have 10 gallons per minute moving down the right side. Now, granted, it's going to move at different velocities when it goes through. For example, if it goes through a very small pipe, it's going to move at high velocity relative to a fat pipe like this. But the flow rate is going to stay constant all the way around the circuit. And what that means is that the weight of the fluid going up in any given amount of time is equal to the weight of the fluid coming down. And essentially, it's like a Ferris wheel that's balanced. And the net effect here is that the circulator only has to overcome the mechanical energy or the head loss due to friction of the fluid. It does not have to lift the fluid up through the circuit. And this is the best analogy I can give you. Think about a Ferris wheel that has an equal weight in each seat. All right? The weight of the seats going up is equal to the weight in the seats coming down over a given amount of time. If that were the case, the only power input to keep that Ferris wheel turning is the power input necessary to overcome friction. Let's say friction in the hub of the wheel, maybe a very, very small amount of aerodynamic resistance. Ferris wheels aren't moving very fast, so that's a very minimal effect. But think about a fluid-filled piping circuit like a Ferris wheel. All right? If we could completely remove all the friction in the bearings of a Ferris wheel and we didn't have any aerodynamic drag, once we got that Ferris wheel up to a certain speed, it would spin forever. It would be a perpetual motion machine. And, of course, you know that that's impossible. And it's also impossible with any real fluid. All right? So perpetual motion doesn't exist. Any real fluid, any water, water-based antifreeze, any fluid that we know of, always is going to create some drag as it moves through a piping circuit, and that's why the circulator has to have power input to keep the fluid moving. Wouldn't it be great if we had hydronic circuits where we could just turn the circulator on, get it up to speed, turn the switch off, and it would just keep spinning forever? We aren't there yet. We're never going to be there. Okay, relationship between head loss and flow rate. I mentioned kind of a classic relationship. It's something called the Darcy equation. You can look this up in any fluid mechanics textbook. If you want to know the head loss associated with flow through a pipe, you need to know the length of the pipe, how fast it's moving, that's the flow velocity. This would be the inside diameter of the pipe. This is a constant. This G is a constant that shows up in physics and mechanics. It's called the acceleration of gravity. And then you also have to know something called the friction factor. All right? And once you get all these, you can put them in this equation and calculate head loss in feet of head. I just want to point out, when you look at an equation, you see an exponent like this, we can say that head loss is proportional to the square of the velocity. What does that mean? It means if we move the fluid twice as fast through the pipe, in theory, we should have 4 times the head loss. Okay? And that's important. head loss doesn't go up in proportion to velocity. It goes up in proportion to velocity squared. So the faster we move the fluid through the pipe, the faster the rate of increase of head loss. Now, I'm going to show you a chart here, and you're probably going to look at this and say, there's no way I'm going to bother using this chart. Well, every engineer that's gone through a fluid mechanics course has probably used this chart a few times. This is how you come up with this number F. This is called the Moody friction factor. You have to calculate the Reynolds number of the flow, and then over here you have to look up the diameter of the pipe and basically follow the curve for a given pipe diameter to where it intersects for a Reynolds number, and you can read over here to the left and get this friction factor. Now, this works, and there are computer programs that will do this for you today, but I want to show you a simpler version of an equation to calculate head loss. And it's based on this, but it's also based on the assumption of smooth piping. And it's derived from some material that you can read about in an ASHRAE handbook. And it's specifically for smooth piping, like copper, PEX, PEX aluminum PEX, any of these polymer pipes that we commonly use in hydronics. And there it is. It says head loss is equal to the multiplication of these three numbers, and I'll show you how you find these, times flow rate in gallons per minute raised to the 1.75 power. That's a simplified version of that Darcy equation. Again, it applies to smooth piping. So most residential, light commercial systems where you're using piping other than steel or black iron, typically those materials, their internal roughness is such that you really should be using the Darcy equation. But with copper or these other materials, simplified version works. It's valid for Reynolds numbers between 4,000 and 200,000. This covers just about the entire range of what residential, light commercial hydronic systems would be operating at. Okay? Now, to do this, we've got to come up with information. We've got to come up with these three values. Let me just go back here for a minute. We've got to come up with values for A, or what's shown here is alpha. And by the way, I use the Greek symbol alpha in the formula, and down here it shows as A. That's just because I didn't have this font. All right, so alpha and A mean the same thing. If you see alpha and A, and you're wondering if there's a difference, it's just two symbols representing the same thing. But we have to find alpha, we have to find C, and we have to find L. So let's start with alpha. If you know the density and the viscosity of the fluid, you can plug them into this, and you can raise it to the negative 0.25 power, and you can calculate it. But here's an easier way to do it. I've given you three curves here. Water, 30%, propylene glycol, 50%. These are common antifreeze percentages in hydronic systems. You just use the right curve. So for water, for example, at 120 degrees, the value for alpha, you can see, is just about 0.05. This is just a graph of that equation for three different fluids for a temperature range from 50 to 250 degrees Fahrenheit. So whether you use the graph or whether you use the formula, you come up with this number. And this is a total description of the fluid. It takes into account its density, it takes into account its viscosity, and implicitly it takes into account its temperature, because density and viscosity both depend on temperature. All right. The next number you have to come up with is the C value, and this gives you all the information needed regarding the geometry of the pipe, the area of the pipe, its cross-sectional area, and it's very simple. Here's the same table or same tubes that we looked at in a previous table: copper, PEX, PEX aluminum PEX, and here's the C values. They've been pre-calculated and just listed in this table. So it's just a matter of, if I'm working with a piping circuit with 1-inch type M copper, the C value is that value. All right? And the last number we've got to come up with is equivalent length. I'm sure many of you have heard of this concept. Equivalent length is the idea that every fitting or valve can be thought of as having a head loss characteristic. And if we could, in our minds, convert, let's say, a 3/4 inch copper elbow. Here's a 3/4 inch pipe size, 90-degree elbow. This says it's equivalent to 2 feet of straight 3/4 inch copper pipe. So the head loss characteristic of that elbow could be replaced by a straight length of 3/4 inch piping. All right? And if we can convert all the fittings and valves, and for that matter, other devices in our piping circuit, if we can convert them over to equivalent lengths of pipe, we can just add those equivalent lengths together and treat the circuit as if it has one total equivalent length. And I'll walk you through an example. Okay. Now, this is just a picture of a portion of a piping circuit. There's obviously more piping behind the wall here, but just imagine we have a circuit. It doesn't really matter what shape or size it is. It's just a closed fluid path that's going to have a circulator. So here's a circuit that I made up, and I'm purposely showing you some lengths of tubing that are in here. It says all the tubing is 3/4 inch copper, and I'm showing you some fittings. Okay, here's some elbows, here's some T's where the flow goes through the side port of the T, here's a swing check valve, here's a globe valve, all right, and here's the flow path that we're following. So let's come up with the equivalent length of that circuit, all right. Well, we go back to that previous slide, and we could, for example, 4 elbows. We've got 1, 2, 3, 4 elbows, okay. Here's 3/4 inch by 90 elbows. We have 4 of them. The table said that each one of them was equivalent to 2 feet of pipe, so that's a total of 8 feet of pipe. All right. We do the same thing for the other fittings. We just tally everything up, and we also add up the lengths of straight tubing here. If we add those up, it's 58 feet. So if we combine the 58 feet with all the equivalent lengths, we're saying that that circuit is equivalent to a piece of 3/4 inch copper tubing that's 100.2 feet long. It would have the same head loss characteristic as a piece of copper tubing 100.2 feet long. Okay? So here's the picture. That's the same circuit. And notice, by the way, I've taken the circulator, I've graded out. There's no such thing as an equivalent length of a circulator. Okay? Just imagine the circulator isn't there. So we're thinking of that entire circuit as equivalent to 100.2 feet of straight pipe. Okay? Now, once we have these numbers, we have the A value, or what I've called alpha, the C value, and the total equivalent length, we just multiply those 3 together because that just becomes a number. Okay? And I'll show you an example of this. That number gets multiplied by the flow rate raised to the 1.75 power. So let's assume we have a water in this circuit at 140 degrees. All right, we've looked up these values. So for 140-degree water from that previous graph, the A value was 0.0475. The C value for 3/4 inch copper from the table was this number, and we just finished calculating total equivalent length, 100.2 feet. All right? So we just put those 3 numbers together. Here's our formula. So it's the 3 numbers multiplied together times F to the 1.75. And if you multiply these 3 together, you get this, 0.295 times F to the 1.75 power. If I just make a table, and I'm going to pick a few flow rates at random, and you can see I've just picked nice even increments here from 0 up to 12 gallons per minute, and then I'm going to use this formula right here to calculate the head loss associated with each flow rate. At 0 flow, we have 0 head loss. At 2 gallons per minute, if I plug 2 in for F, raise it to the 1.75 power, multiply it by 0.295, that's what my head loss is. So I do this for all the flow rates, and I get these head loss values, and then I make a graph. Those circles you see on the graph are just these points in this table being plotted out. Okay? And if I connect the dots, so to speak, into a nice smooth curve, this is called a circuit head loss curve. This is the fingerprint, if you will, of that piping circuit. All right? It's going to become a very important part of sizing a circulator. We're going to cover that in the January Coffee with Caleffi, but for now I want you to understand every circuit has a curve like this, and I just kind of took you through an example of how you'd calculate that. Okay? Now, we can also think about every segment of pipe, every fitting, every valve as having a resistance to it. And here's an example. Here's a discal air separator, a length of pipe, a globe valve, another length of pipe, and a heat exchanger. And I'm representing the flow resistance characteristic of each of these devices by these resistor symbols here. And you recognize these zigzag symbols, like electrical symbols. Well, when we have things in a line like this, we say they're in series, and we can just add those resistances together. If we add them up, we get their total equivalent resistance. We're combining the 5 original resistors in series by adding them together to get the equivalent resistance, just like you would in an electrical circuit. Okay? When you have them in parallel, it's a little more complicated, but still doable. Here's a manifold with 3 gradient panel circuits. Now, these could be, hypothetically, they could be different sizes of tube, although that's not very common, but they can certainly be different lengths. And let's say it's 100 feet, 200 feet, and 300 feet. Well, just intuition tells you that a 100-foot circuit has less resistance than a 200-foot circuit, and so forth. But we can represent these 3 circuits by these 3 resistors. All right, and then we can combine the 3 resistors, which we now say are in parallel, into a single equivalent resistor. Again, if you've ever done an electrical course, you've probably done this. Okay, and there's a formula for doing that. It's a little bit more involved than just adding the resistors together like we did in series. We have to get the reciprocal of each resistor, just divide 1 by that resistance value, raise it to this power, add these together, and then finally raise the whole thing to the negative 1.75 power. I won't bore you with the details of where that formula comes from, but it works, and it's accurate. Okay? So here's the way we think about it. Here's a typical hydronic circuit. It's got some common piping here in orange, and here's that manifold with the 3 circuits. Each of the circuits is represented by these resistors, and then the resistance of the common piping is represented by R4. We're going to combine these 3 in parallel into an equivalent resistor, and then these 2 are now in series, so we can add them together, and we've reduced that circuit down to 1 equivalent resistor. And we can take a very complicated piping circuit and use this kind of analysis to reduce it down. All right? Once we have it, we can find the flow rate in each branch. I'm looking at the time here. I'm going to jump ahead for a quick example. I've just put some numbers into the resistor symbols here. Here's where I've run these 3 resistor values through that equation and reduced them down to a single equivalent resistance value. Then I'm going to add that equivalent resistance to the one it's in series with, 0.5, and we get this value. Okay? Now I want to find the flow rates through each of these branches. I'm going to assume that the total flow rate in this circuit is 5.5 gallons per minute. Now, after January's webinar, you'll know how to find that 5.5. Obviously, that's going to depend on the circulator that we put in over here between C and D. But for now, let's assume it's 5.5. We just want to know how that flow breaks up between these resistors. That's where we plug them back into this formula, and there it is. All right. I take each of those resistors, the 4, the 1.5, and the 9 from here. I take the equivalent resistance of the parallel group and plug it in here. I run them through the calculator, and there's my flow rates. Okay, and if you look at those flow rates, for example, you see the smallest resistance here was the 1.5. Notice it has the highest flow rate, right? A good check on your math is to add those flow rates together, and they better add up to 5.5 or something very close to it. All right. We can also take that total resistance, and we can create the system curve. There's our formula. We just took our total equivalent resistance that we just calculated for that group of resistors. It was this 0.9745, and plug in a few numbers for flow rate, use this formula to calculate the head loss. There's the curve. Again, that curve represents the head loss of this entire circuit. Okay? And again, next month I'll show you how to use that curve along with the pump curve to figure out what the flow rate through that circuit is actually going to be. There are computer programs that allow you to do this. This is one we developed several years ago called the Hydronics Design Studio. And basically, behind the scenes, it's all the math that I've shown you today is taking place. You don't see it, but it's the exact same math. This just kind of cleans it up, makes it faster. Okay? And that brings us up to just about the end of my part. I do want to point ahead here to January 22nd. says analyzing circulator performance in hydronic systems. I kind of think of this as the rest of the story. I've given you how do you calculate the system curve, but the next part of the story is how do you combine that system curve with the pump curve. And this graph right here is kind of a quick summary. There's a system curve. There's a pump curve for a given circulator. Where they cross is where the head input from the circulator equals the head loss from the piping circuit. That's the flow rate the system's going to settle into. So what we've done today is a critical part of selecting that circulator. Back in our head in January, we're going to get into that in more detail. And Bob?
Can I hit us with a couple of questions? I think, Siggy, you're still on board?
Yeah, still here.
All right.
Yeah, John, concerning the Reynolds number, you mentioned the flow rates that result in a Reynolds number greater than 4,000 will result in turbulent flow and therefore good heat transfer if that's your objective through that pipe. Other than geo-exchange, in your experience, are there other applications where perhaps the designer didn't have sufficient flow rate through a tube to get that heat transfer he or she's looking for?
You know, it's pretty tough actually to get below that criteria for laminar flow, but it might happen if you had a situation. Excuse me. It might happen if you had a situation where you had a really long series circuit with maybe half-inch tubing in it, and you're down there in the 0.1, 0.2 gallon per minute range. In theory, if you look at the drop-off, if you switch from turbulent flow to laminar flow, in theory, your heat transfer goes down to about 7% of what it was at turbulent conditions. So be careful of really long series circuits with small tubing diameters. And also, you mentioned geothermal. Because you are running at those low temperatures in some of those geothermal loops, by the end of the winter, you might even be sub-freezing temperatures with 20 or 25% propylene glycol. There are some values. In fact, Hydronic's number 9 has got some minimum flow rates based on those low temperatures, and I think it's based on 20 or 25% propylene glycol. Minimum flow rates that you want to stay above to make sure you have that turbulence. So the geothermal applications are the ones that you really have to be careful about.
Also, on radiant cooling, we talked about, a lot of guys are looking at doing a cooling with radiant now, and that would be, the lower temperatures there would be, we'll talk about that probably more with the pump sizing and stuff next month, right?
Yeah. Chilled water, again, anytime you're going to low temperatures, and especially if you've got antifreeze, probably snow melting application might be another one that comes to mind. At least initially, when that glycol's cold, it's going to move pretty slow at those temperatures.
Okay. Related to the formula that is used to derive the Reynolds number to guarantee good heat transfer, as you increase your flow rate, I think you mentioned erosion could be an issue and some other issues. One of the viewers mentioned noise. Is there any type of, for different types of pipe, any type of noise calculations or flow rates that could result in excessive noise that's a rule of thumbs that are out there?
Well, I don't know of any specific way to calculate, say, decibel output based on flow rate. I'm sure that information exists somewhere, so I'd probably start with an ASHRAE handbook to look for it. But from 2-inch and down, it's the 4 feet per second criteria. And then above that, commonly a 4 foot of head loss per 100 feet of pipe. Again, I'm not sure what decibel level that is based on. It's just it's an industry accepted practice that ASHRAE publishes. Beyond that, you'd have to do some research to see if somebody's actually got acoustic output based on different pipes, different fluids, different flow velocities. I don't know of any.
Okay. And I think one last one, John, and we'll let everyone go. There are some specific questions, Bob, by the way, that we can get back to individually. One comment came in, given heat transfer, it increases as flow rate increases. Given that that's the case, is there any magic about adjusting your flow rate to achieve a 20-degree delta T across your heat exchanger?
No, there's not. 20 20 is just a number that I guess is pretty well ingrained in American hydronics, but it's just a number. There's nothing special about 20 versus 19 versus 21, or you can make the delta T, and we actually talk about this in the upcoming hydronics. We can have, for example, I've seen floor heating circuits operating at delta T's of 2 degrees Fahrenheit because they have very high flow rates going through them. There's nothing really wrong with that if you're not eroding the pipe, and with PEX you can take some very high flow velocities without any fear of erosion. I will mention with copper, in general, you don't want to go above about 6 feet per second in copper tubing. That's where erosion can start to occur. I'm not sure what it is for steel, probably higher. But no, there's nothing special about adjusting for a 20-degree delta T across the heat exchanger based on what we've talked about today.
Okay, very good. Bob, the rest of the questions are concerning the administration. So to answer some of those, if you do want a copy of the PDF, please contact us. And in addition to a certificate, we can get a copy of that of today's presentation out to you. So back to you, Bob.
All right. Well, thanks everybody for tuning in, and also